Good morning. Our report is about the chi-squared test. The chi-squared test is a type of inferential statistic test that measures how expectations compare to actual observed data or model results. It was developed by Carl Pearson in the 1900s. It is also classified as a non-parametric test, and it follows a specific distribution known as a chi-square distribution. This is the test we use to measure the differences between what is observed and what is expected according to an assumed hypothesis. Here are the important characteristics of a chi-square test. This test, as a non-parametric test, is based on frequencies and not on parameters like mean and standard deviation. The test is used for testing the hypothesis and is not useful for estimation. This test can also be applied to a complex contingency table with several classes, and as such is a very useful test in research work. This test is an important non-parametric test as no rigid assumptions are necessary in regard to the type of population, no need of parameter values, and relatively less mathematical details are involved. We have mentioned that the chi-square test is a non-parametric test. There are other terms that we need to discuss, including its counterpart, the parametric test. The parametric test is a test in which the population constants like the mean, standard deviation, standard error, correlation coefficient, proportion, etc., and data tend to follow an assumed or established distribution such as normal, binomial, Poisson, etc. The non-parametric test. The test in which no constant of a population is used. The data do not follow any specific distribution and no assumptions are made in this test. Example: to classify good, better, and best, we just allocate arbitrary numbers or marks to each category. It is also called distribution-free test. Other examples of non-parametric tests are the sign test, the Mann-Whitney-U test, and the Kruskal-Wallis test. The parametric test is actually considered more powerful and versatile than the non-parametric test. As a general rule, investigators use parametric tests whenever possible. However, when there is an extreme violation of an assumption of the parametric test, or if the investigator believes the scaling of the data makes the parametric test inappropriate, a non-parametric inference test will be employed. Hypothesis. It is a definite statement about the population parameters. The null hypothesis states that no association exists between the two cross-tabulated variables in the population, and therefore the variables are statistically independent. Example: if we want to compare two methods, method A and method B, for its superiority, and if the assumption is that both methods are equally good, then this assumption is called the null hypothesis. Alternative hypothesis proposes that the two variables are related in the population. If we assume that from two methods, method A is superior than method B, then this assumption is called the alternative hypothesis. Degree of freedom, or DF. It denotes the extent of independence or freedom enjoyed by a given set of observed frequencies. Suppose we are given a set of n observed frequencies which are subjected to k independent constraints or restrictions. Then df equals number of frequencies minus number of independent constraints on them. In other terms, df equals r minus 1 times c minus 1, where r is the number of rows and c is the number of columns. Critical value. The value that must be exceeded to reject the null hypothesis at the chosen significance level. When the null hypothesis is true, the chi-square is equal to 0. And as differences between expected and obtained frequencies become greater, the value of the chi-square increases. When chi-square is larger than the critical value, then we reject the null hypothesis at the significance level. If it is lower, we retain the null hypothesis or we fail to reject the null hypothesis. Contingency table. When the table is prepared by enumeration of qualitative data by entering the actual frequencies, and if that table represents occurrence of two sets of events, that table is called the contingency table. This came from the Latin word con, meaning together, and tangere, to touch. It is also called as an association table. We have here an example on how to use the chi-squared test if we have one variable. This example pertains to the preference for different kinds of light beer. For example, you are interested to know the difference in preference of beer drinkers when it comes to light beer. So you conducted an experiment with a random sample of 150 beer drinkers, and you let them taste 3 leading brands. The entries came out as 45 subjects preferred brand A, 40 for brand B, and 65 for brand C. Can we conclude from this data that there is a difference in preference in the population? Let's take a look and use the chi-squared test.
So how do we solve for the chi-square? We have here the general steps for solving the chi-square. First is stating the hypothesis. We state our null and alternative hypothesis first. And then locating the critical region. We refer to the chi-square distribution table that will be shown later. And then the degree of freedom, k minus 1, where k is the number of cells or the number of categories, and then identifying the alpha level. Third is we calculate the test statistics. The formula for chi-square goes like this. Chi-square is equals to the summation of the observed frequencies minus the expected frequencies squared divided by expected frequencies. And lastly, the fourth general step is making a decision regarding the null hypothesis. If the test statistics falls within the critical region, we reject the null hypothesis. We reject it if the chi-square is greater than or equal to the critical value. If the null hypothesis is true, then the proportion of beer drinkers in the population that prefers brand A is equal to the proportion that prefers brand B, which in turn is equal to the proportion that prefers brand C. This means that 1/3 of the population must prefer brand A, 1/3 brand B, and 1/3 brand C. Therefore, if the null hypothesis is true, we would expect 1/3 of the individuals in the population and hence in the sample to prefer brand A, 1/3 to prefer brand B, and 1/3 to prefer brand C. Since there are 150 subjects in the sample, the expected frequencies for each cell would be 1/3 of 150. So 50, 50, 50. We must first determine the frequency we would expect to get in each cell if sampling is random from the null hypothesis population. These frequencies are called expected frequencies and are symbolized by Fe, as per our example earlier, 1/3 of 150. The frequencies actually obtained in the experiment are called observed frequencies and are symbolized by Fo. The closer the observed frequency of each cell is to be expected frequency for that cell, the more reasonable the null hypothesis becomes. The greater the difference between the observed and the expected frequency is, the more reasonable the alternative hypothesis becomes. Here we are in our first step for solving the chi-square, stating the hypothesis. Our null hypothesis states that there is no difference in the preference among the brands in the population. More specifically, in the population, the proportion of individuals favoring brand A is equal to the proportion favoring brand B, which is also equal to the proportion favoring brand C. Our alternative hypothesis states that there is a difference in the preference among the brands in the population. More specifically, in the population, the proportion of individuals favoring brand A is not equal to the proportion of individuals favoring brand B, which is not equal to the proportion of individuals favoring brand C. Locating the critical region, we refer to the chi-square distribution table. First, we find the degree of freedom, k minus 1, where k is the number of cells or number of category. So in our example, the degree of freedom which we'll be using is 2, since 3 minus 1. Identifying the alpha level. So we are going to use the alpha level of 0.05. With the degree of freedom 2, our critical value would be 5.991. Calculating the test statistics. So we are now going to compute for our chi-square with our formula. And as you can see, we have here on our table our expected and observed frequencies. So now we are going to compute for the chi-square. 45 minus 50 squared divided by 50 plus 40 minus 50 squared divided by 50 plus 65 minus 50 squared divided by 50. All in all, we will get the sum of 7. Our last step for the chi-square test is making a decision regarding the null hypothesis. So if the test statistics fall within the critical region, we reject the null hypothesis. We reject it if the chi-square is greater than or equal to our critical value. So since our chi-square is 7, it is greater than our critical value, which is 5.991. So our decision would be we reject the null hypothesis. It falls within the critical region, meaning there is a difference in the population regarding the preference for 3 brands of light beer tested. It appears as though brand C is a favored brand. Next up is another example for our chi-square test. A poker dealing machine is supposed to deal cards at random, as if from an infinite deck. In a test, you counted 1,600 cards and observed the following: spades with the number of 404, hearts with 420, diamonds with 400, and clubs with 376. Could it be that the suits are equally likely, or are these discrepancies too much to be random? First, we state our null and alternative hypothesis. Our null hypothesis states that there is no significant difference in the dealing of the suit of the cards. Our alternative hypothesis states that there is a significant difference in the dealing of the suit of cards, and the deck of hearts come up more likely more than the spades, diamonds, and clubs. Our degree of freedom would be 3. We have already subtracted the number of categories minus 1, and we will be using the alpha level of 0.05. With the degree of freedom 3 and our alpha level 0.05, our critical value would be 7.815, which will have to be exceeded by our chi-square. Now we are going to compute for our chi-square. We have already put on a table our observed and expected frequencies. And remember our formula, chi-square is equal to the summation of the observed minus expected frequency squared divided by the expected frequencies. So now let's compute for our chi-square. 404 minus 400 squared divided by 400 plus 420 minus 400 squared divided by 400 plus 400 minus 400 squared divided by 400 plus 376 minus 400 squared divided by 400. All in all, we would have our chi-square value with 2.480. Remember that the critical value that must be exceeded was 7.815. So now, after, we will make a decision with our null hypothesis. Our decision would be we fail to reject our null hypothesis. Since the chi-square value is lower than the critical value, there is a significant difference in the dealing of the suit of cards, and the deck of cards come up more likely more than the spades, diamonds, and clubs. We now have here our last example for computing the chi-square. So, genes that sort independently are not on the same chromosome and not linked if they follow the 9-3-3-1 rule on the 16 square Punnett square resulting from a D-hybrid cross. In this D-hybrid cross, now, we can see the table for the observed and expected frequencies. The total observed is 994, so we found the expected values as to 9 divided by 16 times 994 is equals to 559. 3 divided by 16 times 994, which is 186. And then 1 divided by 16 times 994 is equals to 62. We will now calculate for our chi-square statistics. So, with our observed and expected frequencies, we would have 556 minus 559 squared divided by 559 plus 184 minus 186 squared divided by 186 plus 193 minus 186 squared divided by 186 plus 61 minus 62 squared divided by 62. All in all, our chi-square value would be 0.312. With the degree of freedom 3 and our p-value from the table, which is 0.05, our critical value that must be exceeded will be 7.815. Our chi-square value is much lower than the p-value from the table, so we cannot reject the null hypothesis. The genes assort independently according to a 9-3-3-1 ratio and not on the same chromosome. That would be all for the chi-square test. I hope you learned something from our presentation. Thank you so much for watching. And a big thank you for Miss Janet Bascom for some of the materials for our presentation.